and Misha for setting up this wonderful workshop during this week. So I'm really having a great time here, very intense discussions. And it's also nice to see how different fields come together, and we are all interested in positive scalar curvature in the end. So in this talk, I would like to talk about two topics. One was already mentioned in Misha's talk on Tuesday and at other occasions, namely the link from positive scalar curvature geometry to index theory. And I will shed some light on this topic, especially in the context of non-compact manifolds. And this is related to the coarse index theory of John Rowe. In the second part of my talk, I would like to present you a fairly recent approximation result for Riemannian metrics with low regularity assumptions, C11. And this does not only apply to positive scalar curvature, but also to positive sectional curvature or all kinds of curvature restrictions you might think of, so you will see in a moment. So whereas the first part is more concerning obstructions against positive scalar curvature, so in the second part we are talking about constructions, and that's the flexibility part. It is a little bit in the flavor of H principles. So to start with, this is just an overview of some fairly elementary facts concerning spin geometry and the construction of the Dirac operator. So Misha pointed it out on Tuesday already, drew some pictures on the blackboard. So here's the formal definition. So we are talking about manifolds which have a little piece of more information. Actually, it's not that little. It gives us a lot of additional structure coming from the Clifford multiplication, and that is the notion of a spin structure, which can be defined by prescribing a double covering of the SO frame bundle of M, such that in each fiber we get the natural double covering of spin sitting over SO. So we have a well understood obstruction for that. It's about vanishing of the second Stiefel-Whitney class. So we have this condition under good control. Once we have this piece of information or this piece of structure, we can associate a vector bundle to M, or to the spin representation on delta n. So that's the irreducible Clifford modulo in dimension n over the complex numbers. And this gives us a unitary vector bundle, S sitting over M, which is really directly related to the given spin structure. And now for defining the index, it makes a little difference if we talk about even or odd dimensions. Let me stick to the even dimensional case. It's a little more direct to construct the index in that context. And we notice that when we restrict this Clifford representation on delta n to the spin group sitting in the Clifford algebra, and this actually splits into two irreducible spin representations, the positive and the negative half spin representation, as we call it. And we have a corresponding splitting of the bundle of this spinor bundle S into a positive and negative part. And then we get this differential operator of order 1 that is can be defined in local using local orthonormal frames, EI, by this formula, here using this Clifford connection nabla. And so I define this Dirac operator as acting on sections in the positive spinor bundle, and then it takes values in sections of the negative spinor bundle. And this is due to the fact that here we have a Clifford multiplication with these basis vectors. So this point here denotes Clifford multiplication, and that exists because we have a spin structure here. So this is a differential operator. It's very interesting object because it is a sort of square root of the Laplace operator, and that was already pointed out by Misha on Tuesday. So we have this very important Lichnerowitz-Schrödinger-Weizenburg formula, which tells us that in the presence of uniformly positive scalar curvature on our manifold M, by the way, I do not assume that M is compact here, so this is for compact or non-compact manifolds. I just have to assume that it's actually a complete manifold in my talk. So once we have this uniformly positive scalar curvature, we can derive from this formula a very important spectral property of the Dirac operator, namely because this is a uniformly positive term and this is a non-negative operator, that we get a spectral gap around 0, which is quantitatively more or less described by the number C0. And this is a very useful piece of information because spectral geometry tells us a lot about the geometry and also the topology of the underlying manifold. And so we have the resulting obstruction. So for compact M, let me recall that this operator acting on the positive spinors to the negative spinors is actually a Fredholm operator. This is a consequence of elliptic regularity. And so we can write down the Fredholm index, which is the dimension of the kernel of D plus minus the dimension of the kernel of D minus. So that's an integer because it's a Fredholm operator, and by the famous Atiyah-Singer index theorem, this is equal to a topological invariant of M, the A-hat genus, which is directly related to Pontryagin classes, and so it's well computable. And by putting these two facts in opposition to each other, we can derive obstructions to positive scalar curvature, namely if G happens to have a positive scalar curvature in the compact case M, then this thing here cannot be different from 0. Both of these kernels have to be 0. And then this means so that the A-hat genus actually has to vanish. Because if it does not, then we actually have harmonic spinors, and this means 0 is in the spectrum of D, which contradicts the Weizenburg formula. So this interplay is, I mean, it's very easy to write down, but it's actually quite profound because it gives a pretty subtle obstruction to positive scalar curvature, especially, which is not on this slide now, when we apply this in the context of real bundles and we use real Clifford representations, because then we get an obstruction to positive scalar curvature, which actually depends on the diffeomorphism type of the given manifold. In particular, we get obstructions on certain exotic spheres, not bounding spin manifolds. So this is a brief overview for the compact case. And now when we want to talk about complete manifolds, we can in particular ask about this specific example. So we take the n-2 torus cross R2, and the question is, does this admit a complete metric of uniformly positive scalar curvature or not? So if we took R3 here, then it does, because then we can take a torpedo-like metric. And for R2, it's not so clear. Actually, the theorem says it does not admit such a metric. And it's interesting to notice, if you go back to the classic long article, Gromov and Lawson in the PubMat IHS from '83 about the Dirac operator on complete manifolds, they prove that theorem using enlargeability methods, but they have an additional assumption, namely they need for their theorem that the Ricci curvature is bounded below. Under this assumption, they can prove this statement. And actually, as it appears, this statement is taken up again, revisited in the recent GAFA article by Misha in 2018. And he discusses this on the first pages, actually. And he proves that statement using, as he calls it, width of bands inequalities, which are proven using minimal hypersurface methods. Actually, Misha does, in fact, get more quantitative statement. Namely, he proves that every positive scalar curvature metric on that manifold must have a quadratic decay, and so it cannot be uniformly positive. And it's funny. So in this 2018 article, after stating this theorem, Gromov says in a footnote, Bernhard Hanke told me one can prove this also with Rowe's coarse index theory. And this is actually a discussion which has now been around between Misha and me since for about 1 year. Because so this is related to an article of Thomas Schick, Daniel Pape, and myself, where we apply these arguments for codimension 2 obstructions, and exactly those kinds of obstructions will be presented on the next slides. And this proof or this technique is based on Rowe's coarse index theory, which I find is a really marvelous tool to treat with the positive scalar curvature question from an angle or a point of view that has not been present so much during this week. Namely, it's a large-scale point of view or coarse geometric point of view. And this index theory, this coarse index theory of John Rowe is exactly designed and manufactured to deal with these situations in a very efficient way. You can see, so it's I took a picture here of John Rowe, and he passed away earlier this year. So that I really advertise this theory here may be seen as a tribute to his mathematics here. So let's see. So we start from 2 slides before, and we actually start with the Dirac operator again. That's this operator D that I defined using Clifford multiplication. And so I take as a domain the smooth functions or smooth sections in the spinor bundle over M with compact support, or actually the closure of such sections. And then, or limits of such sections. And then I take the following important fact from functional analysis. And this is actually the beginning of the story, why we have such an efficient setup. Namely, the point is that this operator, this differential operator, has a self-adjoint closure. And it defines an unbounded self-adjoint operator. So this closure is this unbounded self-adjoint operator on a certain domain inside the L2 sections of the spinor bundle. So we are talking about this Hilbert space now. L2 is a Hilbert space, and we have an unbounded operator d bar in a dense domain, and this is a self-adjoint operator. Actually, this is a non-trivial fact. It uses the completeness of the Riemannian metric that we started with, and it uses also elliptic regularity. So it's a non-trivial fact. It's very useful because this implies we have a functional calculus for this operator. And this is especially useful because the functional calculus is directly related to spectral properties. So just recall that applying the functional calculus to such a self-adjoint operator more or less means you apply an arbitrary function, bounded function, to the spectrum of this operator, and you get a new operator with this, exactly this spectrum, which is given by the values of the old spectrum under your prescribed map. And so we can, for example, take this map, which is, it's a real valued function, x over 1 over x squared, and then we take the square root. So that's an odd function which approaches -1 and +1 when we go to minus and plus infinity. And this gives us a bounded operator because we make the spectrum bounded. So this function has tends to minus and plus infinity, to minus and +1. So we have a bounded operator, and we can take a fixed unitary to identify these 2 Hilbert spaces. So this means we get an operator, a bounded operator from L2 sections here to the L2 sections of the same Hilbert space. And it turns out that this is a unitary operator. So it means that this operator times its adjoint is the identity, And but this just holds modulo compact operator, so plus a compact operator. This is nothing more than a different way to express the Fredholm property of that operator D for compact M. And once we have such an equation, we can actually manufacture an element in, as we call it, the zeroth K theory of the compact operator. So this is kind of this difference, or this error term. This K theory is given by projections in the compact operator, so it is the only invariant we have are the integers measuring the dimension of the range of such a projection. So this K theory is equal to Z, and actually turns out that this index we get here is equal to the old Fredholm index we had on the previous slide. Why do we do it in this slightly weird way? Yeah, the point is, and I think that's, I mean, important principle in mathematics. So the Fredholm index was defined as a difference of two numbers, so we get a number, right? But that's getting a number is not a very, so we don't have much structure here. It's much better to view the index as an element of this K theory group, K0 of K in this case, which happens to be equal to Z, because this gives us the opportunity to pass to more general situations and to define indices in more general situations. Maybe this is a little similar as going from Betti numbers, which are just numbers, to homology groups. And we all know that this is a lot better, gives us functoriality and all other kinds of useful properties. So, and but now passing to non-compact manifolds, this Dirac operator is no longer Fredholm. So we do not get an integer valued index. And so it was one of the very useful observations of John Rowe that in this case, the space of L2 sections has an additional piece of structure. Namely, if you have some real valued function on M with compact support, you can just pointwise multiply such an L2 section. And this gives us a module structure of the L2 section over this ring. And the interesting point is this encodes metric properties. So when we are localizing some properties, or we want to localize properties onto certain parts of our manifold, then we can say, okay, let's take a function phi which has support in this or this region, and apply the corresponding module structure here. This means we take an arbitrary L2 section and then we first multiply it with some specific function with some specific support, and then we apply our Dirac operator. So this gives us the possibility to encode metric properties for more general M. And this is really a new piece of information here that goes into that structure or this theory which was not visible before. So it's the C0M module structure. And then we can actually proceed as before, more or less. So this is why I wrote it in that way. We get a bounded operator from between L2 spaces. And these are, we get a unitary operator, no longer modulo compact operators, but modulo locally compact operators. So these are operators which become compact after multiplying them with a function with compact support, or composing with such a section. So this is again by elliptic regularity, and proceeding in the same way, we obtain an index invariant in the zeroth K theory of some more complicated object. It's no longer the compact operators on some Hilbert space, but it is a more complicated C-star algebra, certain closed subalgebra, norm-closed subalgebra of this Hilbert space of bounded operators on L2. So this C-star algebra consists of those bounded operators which are locally compact. So this is what I said before. And the next important pieces of information is that they are of finite propagation speed. This is also important to know that if you have if you apply Dirac operator, so that because this is connected to propagation speed of the wave operator, you have finite propagation speed of the Dirac operator, which very well interacts with metric properties of your manifold. So we have a very nice interplay between several structures, and we also have an index invariant in some K-theories of this C-star algebra. And so we can have some hope that it will be useful. And it's useful exactly when two things happen. It must be computable or detectable in some interesting cases, and we still need some vanishing properties, for example, using the Lichnerowicz formula. And both facts are actually true. So at first, let me give you some little insight how this C-star algebra of bounded, locally compact operators of bounded propagation looks like. So if M is a compact manifold, M, then these are compact. I mean, what does locally compact mean? It means, so we take a map with compact support, for example, the identity, and then the composition with this operator must be compact. So the operator must be itself compact. So these are compact operators, and that's it. So we get an element in K0 of the compact operators, and this means the index is the old index invariant that we got before. Now let's take this metric space. It's non-compact, so it's a discrete metric space. It's the integers with a standard metric. And then it turns out that this algebra is actually given by infinite matrices here parameterized over Z cross Z, so they are infinite in both directions. And the property bounded propagation speed means that the entries of A must be concentrated at a uniform neighborhood of the diagonal. So this means that things cannot move too far away. And then we can work on inductively, and for these lattices we can also compute this C-star algebra completely. We can also write down the K-theory of these C-star algebras, because we are actually now working in a coarse context. This C-star algebra of, we also call it the row algebra of locally compact bounded propagation operators of Rn is the same one as the one for Zn, which we have just calculated more or less. And this K-theory is very simple in the, so this is two periodic. And if we are in the same parity as n, then we get z, and otherwise we get 0, just as in the normal, usual K-theory for compact spaces. And so we get this index invariant, and this actually defines a generator of this group Z. So this is, I think, this example shows us, okay, so there is really a chance to do very efficient computations. And one example is this theorem that we proved 10 years ago together with Kotschick, John Rowe, and Thomas Schick. Namely, we get a slight improvement of the usual enlargeability obstruction by Gromov. Using enlargeability of the universal covering, remember, this means that from the universal covering with a metric induced from M, we have epsilon contracting map onto spheres, which are constant outside of compact subsets, which are of non-zero degree. And this must be true for any epsilon as small as we like. So we have these epsilon contracting maps of non-zero degree for arbitrarily small epsilon. And in this situation, we can use the enlargeability obstruction, the usual one by Gromov, to show that there is no metric which is pi1 m periodic, or in other way, I mean, you could also say there is no positive scalar curvature metric on M. And because this is a completely coarse concept, so this row algebra C star really just depends on the quasi-isometry type of the given manifold. This allows us to improve this slightly and prove that there is no metric of uniformly positive scalar curvature, which is in the same quasi-isometry class of pi1 periodic metric. Why is this an improvement? Yeah, quasi-isometry implies we have a certain Lipschitz constant, but we also have additional constant. We add some constants on the left and the right. And so this means that the identity, in this case, need not be a Lipschitz map. So we cannot just precompose maps going to spheres, epsilon contracting maps with some Lipschitz maps. Okay, so this shows that this is really, now we are in the coarse world. And which makes this interesting, I think, is that there is seemingly two facts that contradict each other. So here we are dealing with spin manifolds. So we have a spin structure on the tangent bundle. This seems to be a very non-coarse concept, I would say. Whereas here we can pass to manifolds inside this index calculation. It is concerning metric spaces only, and we can pass to other metric spaces in the same quasi-isometry class. This is quite fascinating, I think. And now let me go back to the original example in Gromov's paper. So we assume that this product carries a complete metric of uniformly positive scalar curvature. And now we apply the following construction. We remove a small tubular neighborhood around this torus, or this torus cross 0. That's better to phrase it like that. We remove this tubular neighborhood, and then we take the double of that manifold. And this double, metrically, it looks a little, so you could draw it like that. And here we have a gluing region, which is this delta n. So I draw it in that way to make sure or to clarify that here it's not, so we cannot expect that we have positive scalar curvature in that region, although the original manifold, so we assume it has a complete metric G of uniformly positive scalar curvature on the right and on the left. But near this gluing region, it's impossible to do that because we do not have the correct mean curvature condition here at the gluing region. But at least this manifold M carries a positive scalar curvature metric outside of a compact neighborhood of this gluing region. So let's draw it like that. So this is a certain compact neighborhood, which is bad if you wish. And here we have uniformly positive scalar curvature, as well as here. And now we again apply our two facts that we know for Dirac operators. The first is that we have the Lichnerowicz formula, which tells us that under positive scalar curvature assumptions, a certain index invariant has to vanish. And this is also true in the coarse context. Let me go through these lines here. So we have our manifold M. And then there is actually a proper map from this manifold to the reals. So these are the reals. And here the pre-image of 0 is exactly given by our gluing manifold N. So this is our map F. And this means that in the terms of John Rowe, we have a partitioned manifold. So it stretches to the left and to the right with a proper map to the reals. And we have this, this partitioning manifold delta n in the middle of codimension 1. And also, and this is a little technicality, so let me brief. We have a flat twisting bundle for our Dirac operator consisting of 3 rank 1 modules over this group C star algebra, which comes from the fundamental group of delta n, which is nothing but an n-1 torus. So delta n is T n-2, the old torus, cross an orthogonal S1 belt sphere in this R2. Okay, so then we get this index invariant, has to vanish. And also, this is now very nice, we can compute that this index actually has to vanish. And this is a sort of boundary formula for these coarse indices proven by John Rowe. It's the partitioned manifold index theorem, it says that in such a situation, you can read off the coarse index by mapping it to the, actually, I mean, you can think of cutting this apart in the middle, and then we have a boundary map which maps the coarse index. So if this is even, then we are in odd degrees, then we have a coarse index in K1, and the boundary map maps it to K0 of the corresponding index of this compact manifold. So it's a usual Atiyah-Singer index, which we can compute. And once we know that this index doesn't vanish, we see by functional reality that this coarse index doesn't vanish. So we have a non-vanishing of this index invariant, but it must be 0 by the Lichnerowicz formula, and so we get a contradiction. There is one fascinating feature here, especially when I draw the picture like this, namely, so for computing the index, we use this partitioning region here, delta n, which sits inside the compact neighborhood where we do not have positive scalar curvature. I mean, we could easily move this partitioning manifold to the right or to the left in order to avoid this picture. But nevertheless, when we draw it like that, then we see it's very nice how the two effects work against each other in this coarse index theory. Namely, in fact, the vanishing of the index here is really a coarse property, and compact perturbations, or a region where we have non-positive scalar curvature, which is compact, does not affect our computation in any way. So this is a partial vanishing theorem by John Rowe, saying that this index here actually has to vanish even if we have positive scalar curvature just outside of a compact subset. This is again an incarnation of this coarse concept here.
Can I ask quickly, the region where the R doesn't have to be positive just means it's volume controlled to get the L2 bounds? Or
It must be a compact subset.
does it need a uniform bound on volume? Or
Volume is, it's, I mean, you mean if we have a nose like that sticking, it's a, yes and no. I mean, we have to discuss this a little bit more in detail. It's not completely obvious.
So it's not just coming from the L2-ness?
No, it is. It has to do with really with local compactness of the operator. Yeah. And now let me cite a theorem which is now more general. So we have a general codimension 2 obstruction using Rowe's index theory. And namely, we assume we have a spin manifold with a codimension 2 submanifold, which has trivial normal bundle. On pi 1, we must be injective. On pi 2, we must be surjective. And we assume that the ahead genus of the submanifold is non-zero. So this submanifold of codimension 2 is now meant to be the obstructor to positive scalar curvature, and under these conditions, actually, M itself does not admit a positive scalar curvature metric. And I find this interesting because we can, it's more direct to write down the corresponding codimension 1 statement. If we have a spin manifold, a codimension 1 manifold, which represents a non-zero class in the n-1st homology, and has non-vanishing ahead genus, and this manifold does not emit a metric of positive scalar curvature. Within spin geometry, that's not very hard to prove. And, but this statement is completely analogous to the one that we are interested in the non-spin case using minimal hypersurfaces. But I really want to point out that here we have an overlap of results concerning this result here, which we can approach from fairly different angles, minimal hypersurfaces here, Dirac operator methods there, and I think it's not understood well or not at all how this interaction between these two methods actually works. So it's an observation that we get also this same kind of result here. And concerning this codimension 2 obstruction, I think there is no analogy of that without the spin condition. as far as I know. So this really points into the direction that we have strong homological properties of K theoretic invariants and this index invariant of rho, so that we can prove such a statement, which, by the way, generalizes a statement of Gromov and Lawson from their 83 paper, which is a marvelous piece of work. I mean, we are still studying this paper in a way and trying to understand it step by step. So this is my account of the index theoretic methods apply to non-compact manifolds. And now let me pass to a constructive side. I would like to discuss the following fairly general approximation theorem. So we start with a differentiable manifold, V, together with a C2 Riemannian metric. Need not be complete, just some Riemannian metric. And now we want to approximate this metric by metrics with better curvature properties. Namely, we fix a strong, a neighborhood in the strong C1 topology of that metric. So we control up to first derivatives. And then we find a new Riemannian metric G hat on V, which has the following properties. It doesn't have C2 regularity anymore, it just has C11 regularity, but it's remarkable so that the first derivative is still Lipschitz, a Lipschitz function. So usually in these approximation results we get C1 alpha regularity, but here we have C11 regularity, which is just below C2. So this new metric can stay in this prescribed neighborhood. And because we have C11, the second derivative exists almost everywhere by the Rademacher theorem, so we can write down the curvature tensor as a L infinity tensor field, which is essentially bounded. And this means we can define sectional curvature almost everywhere. And this can be, for example, prescribed by being larger or equal than 1 on an open dense subset of V. So that's the crucial property, because unless writing this, I mean, we get a contradiction here. I mean, I'm not saying that every manifold admits a C11 metric of sectional curvature bounded below by 1, but we can do almost as good. We can say it has this property on an open dense subset of V, which is also a pretty large region, I would say.
Every open manifold admits that.
No. Every manifold. Every manifold. Let me go on with the discussion, and this will be taken up at this point. So the first thing is remarks to put this result into context. The first thing is we cannot require that G hat has regularity C2 because in this case, we would have sectional curvature defined everywhere. When it's bounded below by 1, on an open dense subset, it must be bounded below by 1, and this would contradict the fact that there are many manifolds without positively curved metrics. So I mean, it's not, we don't have a direct connection to the Nash-Kuiper theorem, but it is, in a way, of a different flavor, so to speak. Namely, we are talking about Riemannian metrics of low regularity, and then counterintuitive effects can happen. For example, we have the classical Nash-Kuiper theorem that every short C1 embedding, Lipschitz C1 embedding, of a manifold into Euclidean space, dimension n+1 at least, can be C0 approximated by isometric C1 embeddings. So this is a very strong counterintuitive result. And here we cannot have C2 regularity either, because this result says we have isometric embeddings into arbitrarily small balls in Euclidean space. And if such an embedding were C2, then this implies that the sectional curve of M at some point has to be very large, because we compress it into some small ball. So C1 regularity is the best we can get here, or almost. I think there are also improvements of that result, but we cannot get C2, and we cannot get C2 in our result either, for similar reasons. And we cannot require this G hat to have curvature bounded below by 1 everywhere, even not with the C11 assumption, because actually we have a diameter bound for C11 metrics. And so this would imply that we cannot have manifolds with arbitrarily large diameter with this regularity. So the property that it is bounded below by 1 on an open dense subset only, this is essential. We cannot get rid of that. And I mean, we can work with other curvature bounds. It's a very flexible argument, as you will see. Talk about negative curvature or whatever, also pinchings. And we can also work in an extrinsic setting, working with embeddings into Euclidean space and with the induced metric. And so just let me point out this corollary. Every smooth manifold of dimension at least 2 admits a complete Riemannian metric, C11 Riemannian metric whose sectional curvature is bounded below by 1 on an open dense subset. It's the same statement as before, but I just kind of condense it to this statement, and we have a complete metric because actually every smooth manifold emits a complete metric. So we can start with that metric, apply the approximation result, and if we stay C1 close to a complete metric, it stays complete. So the H principle of Gromov says that every open manifold has a C2 Riemannian metric of sectional curvature bounded below by 1, but this is in general incomplete. I mean, we have this H principle. We get a metric has this property everywhere, but it cannot be complete for obvious reasons, because then we have obstructions. And also here it's interesting consequence. It's a little mind twisting. So let's start with compact surface of higher genus in dimension 2. It will turn out that this metric G hat is actually a C0 limit of smooth metrics. And the Gauss curvatures of these metrics, which cannot be positive because we have high genus, they converge weakly in some LQ space to the Gauss curvature of this C11 metric G hat. We can take any Q in the open interval from 1 to infinity. And then we can write down this computation. We get an integral over K hat. So here we have the volume density of our limit metric G hat. And because we have a weak convergence, we can pass to the limit under the integral sign here. And here we have the Gauss-Bonnet formula. This means that this integral is negative, although the Gauss-Bonnet formula holds for C11 metrics G hat. So seemingly we have a contradiction here. Does anybody see how this is resolved?
Not a contradiction, is it?
Why?
I mean, like, because your theorem is in almost everywhere, right? I mean,
Almost everywhere.
sorry, yeah, you're right.
Other suggestions? That's now.
Maybe he's only converging it on Q and you're integrating.
That's okay. So that's not a problem. I mean, we converge it so we can pass under the integral sign. That's okay. There must be another reason. So I leave that open. So I mean, here we have seemingly a contradiction. This is not so good, but there is a fairly direct explanation why this is not a contradiction. So it's bounded below by 1 on an open dense subset. So this is what we have for this metric, for this Gauss curvature K hat. And let me now indicate how we prove that statement.
Sorry.
Yes.
Sorry for interrupting.
Yeah. No. Go ahead.
Be used to smooth Alexander spaces.
I don't think so.
Because he said he didn't satisfy the diameter condition.
Yeah. Okay. Sorry. I would like to give you an idea how we prove such an approximation statement. And we use a result by Gromov. Actually, it's not proven by Gromov, but stated by Gromov. He calls it the weak flexibility lemma. And it concerns partial differential relations, right? So we are talking about solutions to partial differential relations here. And just a quick reminder, so we talk about K jets of smooth functions defined on open subsets of Rn with values in R big N. And so the kjet means the collection of all partial derivatives, mixed partial derivatives up to order k. And using that information, we can define a kjet bundle whose typical fiber over point V is all possible kjets of functions or of sections in that bundle near little v. So that's the kjet bundle. And then we talk about partial differential relations of order k. These are just subsets of the total space of this kjet bundle. We say a section solves this relation if the kjet of this section lies in the relation. And recall that we can write down curvature restrictions and many other kinds of geometric topological properties in terms of that language, right? Because, for example, the sectional curvature can be written as a second, in terms of second derivatives of the Riemannian tensor, and so this gives some restriction on the 2-jet of some of the section of the bundle given by symmetric bilinear positive definite forms on the tangent bundle. And now there is an interesting statement which appears in Gromov's book on the subject on partial differential relations. He calls it the weak flexibility lemma. We call it local flexibility lemma. I think it's a little bit more appropriate. And it says the following. So we start with some smooth fiber bundle. It's a very general statement. We take a smooth submanifold in V, which has to be closed as a subset. So here it's just a schematic picture. We have V, it's the reals, and V0 is this closed submanifold, which is in this case just a point. We take a partial differential relation, subset of the kjet bundle total space, and we have to assume that this is open. And then we start with a solution. For example, we have a given metric with some properties, a solution or relation. So this is this F0 here. This is the solution, the given solution. And then we start deforming that solution locally. This means we have a continuous path defined on the unit time interval with values in CK sections over a smaller subset U. This is this blue region. And we get this family of sections which satisfies the given relation. So that's a local deformation of our solution. And in addition, we have to assume that the k minus 1 jet stays constant at this point. And this is the case in this picture. So this is the given data. And now the local flexibility lemma says we can extend this deformation over the whole of V while staying in the relation. It's a very general, extremely useful statement. And that appears in Gromov's book about partial differential relations. So Misha pointed that out to me when I was talking to him last year, wrote me an email, look at exercise, what is it, 5.2 H prime on page 111 in his book. And there is this, it's formulated as an exercise in a way which is a little confusing, I would say. But basically it is this statement. In this given situation, we find a smaller subset U0 of V0 such that we have a global deformation of our solution all over V. And in V0, it's the given local deformation. Outside of U, we stay constant. And then we have a certain interpolation region, which is indicated by that picture here. And the point is that we can extend this deformation in such a way that we stay in the given relation. And already this picture is a little, it's quite interesting when you think about it. For example, you can talk about the relation given by saying that the second derivative is positive, right? We are talking about convex functions. Then we have this local deformation here. All these functions are convex. And this picture here is a little misleading because here this interpolation region is not a convex, doesn't satisfy convexity. But still the theorem holds. So this picture is misleading because we must apply this interpolation in a much smaller region And when you think about it, it is possible to connect these deformed solutions with the given one in a very small neighborhood while staying convex. And this is a nice exercise that you can carry out in your head. And you see it's not completely obvious that you have enough space there. And in this way, it's a basic assertion in jet bundle geometry. Or, I mean, it's maybe an advanced exercise in calculus, so to speak. And interestingly, the statement reappears in his 2018 article. Again, without proof. He says, just do it for one-dimensional V, and the rest is more or less trivial. But that's, I would say, it's not really true. I mean, that's a little mean. It's not so easy to prove here. And so the basic idea of the proof is the following. We introduce an interpolating factor in front of the t parameter for this deformation. So this function here is a cutoff function, which is indicated here. And this is 1 in a small neighborhood of 0. It's 0 outside a bigger neighborhood. So when this thing here is 0, then we are constantly equal to f0, right? And this interpolation region exactly corresponds to the value of this v parameter here. And now the point is that one has to find or write down this function, or find a function which has good properties so that actually this deformation stays in the given relation. And so it's an open relation. Let us see. So if we take derivatives of such a thing, then we get the derivative of this thing, of f, which is in the relation. That's an assumption. And then we get certain terms coming from the chain rule, which we have to add. And these terms, which involve derivatives of tau, they have to be made arbitrarily small. So, and then we can stay in this open relation. And the crucial property is that this function, this interpolating function T epsilon, must have this property here that the kth derivative has to be bounded above by ck, that's a constant, divided by rk. So this rk cancels when we take the kth derivative of the function f, because this is then will stay constant here. This is the assumption. And then, or will actually, so the kth derivative can be estimated by a constant. And then we have this additional term here in the denominator. And this can be made arbitrarily large, this ln epsilon, when we choose epsilon small. That's the point. So we can make this term here arbitrarily small even after multiplying it with r to the k. And then things cancel in a nice way, and we are basically done. So the technical proof is then a little bit more difficult, because if we have a non-compact V, we have to cover it with small balls, and we have to work with different epsilons associated to a partition of unity. But in principle, that's the idea. And just some remarks concerning the results. We can also work with higher regularity requirements for F0, and especially the deformation F. I was talking about continuous deformation. We can also talk about CL differentiable deformations, and then the extended deformation little f, so this is this extended deformation over a whole of V, will also be of the same regularity. So this condition that the k-1 jet stays constant cannot be dropped. You can see that easily for the case k equals 1 already. Namely, if you say we have the condition that the first derivative of our function has to stay very small, and now you take a solution, for example, constant function 0, and then we started deforming near the point 0, and we take a constant function whose value changes. For example, it gets constant to 1 in a small neighborhood, then we cannot connect this to the given function while staying in the relation. So we are not allowed to change the k-1 jet. And also, so I said that V0 must be a submanifold. this is an interesting point because Misha says in his 2018 paper in a footnote, probably we can work with just closed subsets. And I think that's not so easy to see, so we didn't quite get that. We can prove our statement for, as we call it, k distance regular subsets. And this means we have a certain property of the distance function to the subset V0. The property is that we must be able to find a CK CK differentiable function in the complement of U. So we remove V0. So it must be CK regular, which is in general not the case if we just have a closed subset. It must be. It must sit between our distance function and our distance function plus eta, which is some prescribed threshold, and we must especially have this property for Lth derivatives. And this this bound for Lth derivatives, this holds if we assume that V0 is actually a smooth or CK plus 1 regular submanifold. Then this is true, but I think it's, I mean, this is an open point, so to speak. It's not clear to us what closed subsets of a smooth manifold V have this property, that we can approximate the distance function by functions R eta with this property, with these two properties. So we have, so this means we have to be close to our actual distance function, and then we must have these bounds for Lth derivatives. And I think this is an interesting question. So for k equals 1, this is, there's nothing to prove because the distance function is Lipschitz. We can then approximate it by a smooth function with bounded derivative. So here we have 1 minus 1. That's fine. But for higher regularity, that's not so clear to us. OK, so this is some point that is left open here in this context. And now let me prove this theorem using the local flexibility lemma. Here's a reminder. We have a differentiable manifold. We take some Riemannian metric of order C2. We prescribe some C1 neighborhood in the strong topology. And then we get a new metric G hat, which has these properties. It's C11 regular. It stays in this neighborhood, so it's close to our given metric. And this metric tensor has the strong curvature property on an open dense subset. So it consists of 3 steps. The first one is a local or infinitesimal, or no, actually a local computation, because we want to apply the local flexibility lemma. So we start with our metric G, and then we start to deform it locally. Then we can extend these deformations, and this will be then repeated. How does it work? In general, let us start with some Riemannian manifold V, and we take a point P in that manifold. And I assume now on this slide that the sectional curvature at P is bounded above by 2. So this minus means it is the minimum of sectional curvatures of all 2 planes at P. So this is this minus here, 2 planes at P. And then we develop the metric tensor in normal coordinates around P. We have the second order term involving the Riemannian tensor. And we can write down in the same coordinates a metric with constant sectional curvature K, right? Then we can just interpolate these 2 metrics. Locally, this is fairly, I would say it's just drastic. So we take affine interpolation of the second order term here and the same for the remainder terms. OK, so this gives us a family of Riemannian metrics in a neighborhood of P. And at the point P, actually, I get an affine straight connection or affine homotopy between the sectional curvature of G and the constant sectional curvature K here. And when I move away from P, I get, this is no longer a direct straight connection, but it's almost like that. And this is written down in these 3 lines here. So F0, so this local deformation here, when I plug in t equals 0, then I get the given metric G, and F1 has constant sectional curvature 2 around P. This is then this metric. And the one jet stays constant at P. This is good. And also, it's important to notice that for each epsilon, I can take this normal neighborhood so small that the loss of sectional curvature is bounded above by epsilon. Because actually at the point P, there is no loss of sectional curvature whatsoever because of this condition. And so I can pass to a small open neighborhood so that this error term is bounded above by epsilon. And I take this as my relation that this property holds and go into the local flexibility lemma. So this is the local flexibility lemma. We get a family of C2 Riemannian metrics which are defined on the whole of V, starting with the given metric little g. So on the smaller neighborhood U0, a little smaller than U, I have my deformation from the previous slide. In particular, at time equal 1, we have constant sectional curvature equal to 2 on that neighborhood U0. And now that's the nice thing, the loss of scalar curvature is bounded above by epsilon on the whole of V. And this is the interesting effect of this local flexibility lemma. We can gain a lot of curvature concentrated near P, and the total loss of sectional curvature is bounded above by little epsilon, and we can choose epsilon as small as we wish. When we get a smaller epsilon, then U0 has to be taken smaller. And so in particular, we get a new Riemannian metric on our manifold V, which has these 2 properties. On this neighborhood U0, we have constant sectional curvature 2. And let me draw a little picture here. And the total loss here is bounded above by epsilon. So here we have our point P. And then I have this neighborhood U0. This is U0. And here the sectional curvature is equal to 2. And outside, the sectional curvature is bigger than the sectional curvature of G minus epsilon. And here I take the metric G twiddle P epsilon. Right. G twiddle P epsilon. That's the situation that we have here. And right, so this is what the local flexibility lemma gives us. And we apply this to an iteration procedure in the following way. We choose a countable dense subset P1, P2, and so on sitting inside V. We start with our given metric, G. And then we take smaller and smaller epsilons. They are bounded above by 2 to the minus nu. And the point is that the geometric series tells us the sum of all those is bounded, or it's equal to 1. So these errors will accumulate, but the accumulation is bounded above by 1. And now the iteration procedure works like that. So if the sectional curvature minus at the point P nu when we pass from nu minus 1 to nu is bounded above by 2, we apply the previous step, and then we get a new metric looking like that around P nu. And if this minimal sectional curvature was already bigger than 2, then we leave it as it is. So this means this new metric has sectional curvature bounded below by 2 on some open neighborhood. This is this U0, and I call it here U nu around P nu. And also the error that we create is bounded above in general in sum by 1. So this means when we pass to some arbitrary higher mu, then the sectional curvature of this metric G mu is bounded below by the sectional curvature of G nu minus 1. And that's because the sum of all these mistakes is equal to 1. Okay, so then we can actually assume that the sequence is locally bounded in the C2 norm and stays in the given C1 neighborhood of G. We can actually add this to our relation. Then applying some standard approximation techniques using the fact that this space is reflexive, we find a weakly convergent subsequence at first on compact subsets, and then we apply a diagonal argument, and here we get a weak limit G hat metric. And actually, because pointwise inequalities persist under weak convergence, this limit metric still has the Lipschitz property, or the first derivative is Lipschitz. This is this G hat. And by construction, the sectional curvature is bounded below by 2 minus 1 equal to 1 on this union of all these open neighborhoods of this point P nu, and that's an open dense subset. And so this finishes the proof of this approximation theorem. So that's the end of my talk. I thank you for your patience.